So what does it mean? What I am telling? I am telling is that suppose I have for the element A, I get two elements B and C, such that B star A is equal to E, and I am telling C star A is equal to E. What the conclusion I can make? Conclusion make is that B must have to be equal to C. And if this B and C are not equal, then you can say no. The inverse of the element A doesn't exist for the set S with respect to the binary operation star defined on it. Clear? So identity element on a set is unique. For all element A belongs to S, I always get this one. And inverse property is this one. There is something called composition table, which is very helpful when we discuss about that whether set S and a binary operation star defined on that set S satisfying these properties or not. Okay, what are the properties? Associative property, commutative property, identity property, and inverse property. Composition table, sometimes in other way it is also known as a multiplication table, like that it will be very helpful to decide whether it is satisfying associative property, commutative property, identity property, and inverse property or not. We will see how we are going to achieve this, but before that I will suggest you to have a look into this for 2 minutes. Alright, so let's see how a composition table is constructed and how it leads to conclude us whether these properties are going to be satisfied or not by looking into the composition table. So let us define a set S which contains 4 elements: 1, minus 1, I and minus I. What is I? I is the equal to root over of minus 1, that is the imaginary number, right? We will discuss in details when we will study complex numbers. Okay, all details about I. And an operation defined on it is actually a multiplication operation, normal multiplication, right? Then we can construct a composition table. How we can construct a composition table? Let's see. So to construct the composition table, we will write one vertical line and one horizontal line. And here we will write the operation star. Along the horizontal line, I will write all the elements: 1, minus 1, I, minus I. Along the vertical line also, I will write the same elements in the vertical manner: 1, minus 1, I, minus I. And for the sake of simplicity, we can make a horizontal line here. And here also we can write the vertical lines. And for beautification, we can complete this thing. Now what we will put inside in all these cells is that the output of the operation, okay, that the operator star on these elements. What does it mean? It means that, okay, if I multiply 1 and 1, I get 1. 1 and minus 1, I get minus 1. 1 and I get I. 1 and minus I, I get minus I. Minus 1 and 1, I get minus 1. Understood? Right? So what I am doing here is that in this matrix I am just seeing what are the elements in the horizontal and vertical lines are coming. These elements I am making a operation star on those two elements, and result value, the resultant value I am keeping in this matrix. Okay. So minus 1 and minus 1 is 1. Minus 1 and I is minus I. Minus 1 and minus I is I. I and 1 is I and minus 1 is minus I and I is I square, and I square is equal to minus 1. And I and minus I is equal to minus I square, that is become plus 1. Okay, so understood, right? So what is I? I is equal to root over of minus 1. So I square is equal to obviously minus 1, and minus I square is equal to plus 1. And minus I and 1 is minus I. Minus I and minus 1 is I. Minus I and I is minus I square, which is plus 1. And minus I and minus I is plus I square. Minus I into minus I plus I square. Plus I square means is actually minus 1. So I have actually made the composition table on the set S, and the normal multiplication operations are defined on S. Now, how we can conclude that by looking into this composition table whether this set S with respect to the operations are satisfying this property or not? Okay. First thing is that whether it is a binary operation or not, how we can define, how we can conclude. You see all the elements which is marked in the red color in this matrix belongs to the set S. Right? So that concludes that yes, it is a binary operation. How we can conclude? It has identity element. Okay. You look into that row or that column which is exactly matching the number of, suppose let's take the row, particular row. The number of elements in the row, the position should match with the topmost row which is there in the, which I wrote in the black color. That means what is happening here? Suppose you see the element 1. What are the things are going in the red color? 1, minus 1, I, minus I, which is exactly there in the topmost row. 1, minus 1, I, minus I, which I wrote in black color. And here it is in red color. The elements what I received after making this operation. Similarly, you take this column 1 and you see the position of 1, minus 1, I, minus I exactly matching with the leftmost column which I read in the black color. So that tells that yes, 1 is the identity element. For rest of the elements minus 1, I, minus I, their position is not exactly the position of minus 1, I, 1, minus I are not exactly matching with the topmost row. So you see, by looking into the composition table, you are able to understand that how to find the identity element. Okay? How to find the inverse element? Very simple. The moment you know identity element, it is finding the inverse is very easy. And the thing is that you see, you can only go for finding an inverse if the identity element exists. If identity element doesn't exist, there is no point of proceed further to find the inverse of an element. The moment we found that 1 is the identity element, then you found what is the identity element of 1 is 1. What is the identity of minus 1? I will see that where I am getting 1. Then I will find the corresponding element in this vertical topmost row. So, and that will be the inverse of that element minus 1. So what is that? Minus 1 I am seeing here, I am getting 1 here, so I will go in this way minus 1. So minus 1 is the inverse of minus 1. What is the inverse of I? I see I will go there where I get the identity element, I get the identity element here. Then I will go here minus I. So identity inverse of the element I is minus I. Then I will go to minus I will go, I will get 1 here. Then I will go along this one, I will get I. So inverse of minus I is I. Clear? So we are able to find the inverse property, whether this set with respect to the operation holding true or not, by looking at the composition table, identity property. Now we are going to see the commutative property. How you can see the commutative property? Very easy. Along the diagonal, you just suppress this along this diagonal. Then whatever the element you are getting here in this portion, in this lower matrix, okay, will be exactly the replica in this upper matrix. So in a more practical way, if I see, if I put a mirror here along the diagonal, okay, and if I get the reflection of this matrix here exactly, you see, minus 1 is here, I get minus 1 here, I here, minus I here, minus I here, minus I here, minus I here, I here, 1 here, 1. That means if you just, with respect to this diagonal, if you fold that lower triangular, okay, matrix, you will get the upper triangular matrix. So what I am saying is that vice versa, obviously the upper triangular matrix if you do, then you will also get the lower triangular matrix. So these two triangles, okay, are exactly same. Means if you flip the one, you will get the other. As we are getting, then you can say yes, this operation is a commutative operation. If the replication, if this lower triangular matrix is not the exact replica of the upper triangular matrix, then you can say yes, commutative property is not going to be hold true. That means the set S with respect to the operation star is not a commutative property. It's not commutative. Similar way of saying this thing, that the operation star is not commutative, we can say commutative property is not going to be hold true, like that, by looking into the composition table. Right? Okay. Alright. So what I suggest you is that just have a look into this example and see how it is actually satisfying these properties. One thing, in case of any smallest doubt, okay, please do send me email. Okay. So here is my email ID. I write it here. It is konar.classes@gmail.com. Because confusion may come, right? So at that time you just call me. Just send me email and we'll have a discussion. I'll call you as and when required and make this understanding very clearly, because this composition table is such important thing, it's such a beautiful feature to conclude whether these properties are going to be true or not. So it needs a very solid understanding. Yeah, there is one drawback is there, small drawback here. If the set S is not countable, then you cannot conclude whether this property is going to be hold true or not by means of this composition table, because you cannot compute the composition table, right? Because the set is not countable. It has a infinite number of elements. Not only that, if it has a huge number of elements, suppose 100 elements, if the set S contains, then 100 by 100 matrix computation is not that easy. Okay, thank you. So our last topic here is that algebra of real functions. Okay. Real functions, that is the important part here. So let's define two functions. One is f, it is a x to r, and another function g, this is also from x to r, where x is a subset of r, correct? More precisely to say, x can be a proper subset or improper subset, whatever. Now, f plus g is a function. So f plus gx will be fx plus gx. Similarly, f minus gx will be fx minus gx. F into gx will be fx into gx. Alpha into fx. Okay. Well, let me write very clearly. Suppose I got a constant alpha. Alpha into f, x is equal to alpha fx for any constant alpha, and fx by gx, I'm sorry, I am going to write f by g into x is equal to fx by gx, where gx is not equal to 0, otherwise it will be undefined. Now, the point is that the domain of this function, okay, of this composite function, what it will be. Suppose d of f is actually domain of the function f, and d, g is the domain of the function g, right? Then for all these cases, the domain of these functions will be d of f intersection of d of g. Clear? Alright, so this algebra of real functions are important especially for IIT joint entrance examinations. Okay. This is the end of our topic in functions. Any smallest question, any kind of question, please do not hesitate. Send me an email here and I will call you back. We'll discuss in details. Thank you.